Yes, and we are live, I think. Hi, Volviane. Um, can you hear me? Can you hear me?
Yeah, I can hear you.
Okay.
Yes, I can hear you.
Okay. Okay. I had an echo here. Let me just fix that.
Hello. Hello. Can you hear me? I think your
Oh,
mic is
my
moving
sound was
something.
off. Yeah, yeah. I had a little technical difficulty from the side. Okay. Hi, everyone.
Okay.
I think we are welcome to this new edition of KmerAI Talks. And we are today. My name is Jonas Nyawe. I am your host today. Uh, it's my pleasure to host Volviane today for this talk. Hi, Volviane. I hope everything is set up on your side.
Yep. Hello.
Yeah,
Hi,
yeah,
all.
yeah.
Welcome.
So yeah. First, I think we will. Hi, everyone online. Hi, Lupe, Emma. Hi, Futse. Hi, Idris. Hi to everyone that is connected. So the way it will go, I think it will be as usual. You will go through your presentation, and then we will take the questions at the end of your presentation, uh, if that's fine with you. So I'll present you first. So our guest today is Volviane Saphir Fogo, who is currently pursuing a PhD degree in the Faculty of Science and Department of Mathematics and Computer Science at the University of Dschang in Cameroon. And she is working on machine learning and cybersecurity under the game theory and machine learning for cyber deception, resilience, and agility, short for GMCDRA, which is a project sponsored by the US Army Research Lab. She's an African Master in Machine Intelligence Army alumnus, where she obtained a Master of Science in Machine Learning, which is a master sponsored by Facebook and Google. And before joining Army, she obtained a Master in Science in Mathematics from the African Institute for Mathematical Sciences. So today she will be presenting us her work on an application of machine learning in cybersecurity. So it's AIIPot, if I present it, I think Adaptive Intelligent Interaction Honeypot for IoT devices. So Volviane, you have the floor and welcome. Volviane, hello? I don't know if Volviane is went offline. She had some internet issues before. Hello? Hi, Volviane. Yeah, I think she's having uh, a bit of trouble with the internet. And that's also why her camera is off. So, yeah. Yeah, she went offline. So I think we'll wait a little before that she comes back online. Mm, thank you for the patience. I'm just, let me just, yeah, let me check on her. I'll be back soon. All right. Think Volviane is back.
Yeah, I'm back. So sorry
Yeah,
for
yeah,
this.
yeah.
Just having some technical issue. Okay.
No
Please,
problem.
can you see my screen?
Yeah, we can see your screen. Um,
All right.
yeah.
So, can I get
You have,
started?
yeah, you have the floor.
Okay. Thank you. Thank you so much for the introduction, and thank you so much for inviting me. So, and thank you all for coming all that live. So, it's actually a great pleasure for me to present the result of our research on adaptive intelligent interaction honeypot of IoT that we call it AIIPot. And this work was actually conducted under the guidance of Professor Marcelin Kenlifat, Professor Alain Zamko, and Dr. Laurent Gila. So we may take questions at the end, right? And please feel free to stop or write to me off if I'm not online anymore. So I just want to confirm. Can you still hear me?
Yeah, yeah, yeah. We can hear you.
Right.
I'll let you know if anything happens.
Okay.
Just go
Thank you
ahead.
so much. So okay. So let's get started. So actually, this year 2016, a year that actually changed how we see the Internet of Things. The Mirai botnet attack took advantage of weak security in IoT devices, and IoT here stands for Internet of Things. And those IoT devices like camera and router, and the Mirai botnet turned them into tools for marketing. This attack actually brought down big websites like Twitter, Netflix, and CNN with powerful DDoS attack, which is actually was one of the most powerful attack in the world right now. So it was actually a clear warning. Our everyday smart devices are now targeted by cyber criminals. So this actually shows us that the weaknesses in IoT device could actually be used against us. So how is this even possible? So actually we are going to understand this through this presentation that will be structured as follows. First of all, we will have an introduction which will present us a kind of background and the motivation of this research, followed by the related work, which actually review existing IoT security strategy and their gap. And after that, we will delve directly into our proposed approach and the result, which showcase our new security measure and their impact. And then we will conclude. So let's get started. Recently, this is 2 months ago, a report released by the major cyber attack, showing that since 2016, IoT vulnerability are still a big issue that still need to be solved. So, in the rush to bring product to the market, usually manufacturers overlook security that leaves device
Uh,
exposed. And
Excuse,
also, many of us, yeah,
uh,
yes,
we
please.
lost you for 5 seconds. Just to let you know. Uh, but sorry for the interruption. But just I wanted to let you know that we lost a bit the intro in that part. There were shortcut. I don't know if some people online had the same issue I have. So I didn't get the full uh, things you said on on this introduction here. So if you don't mind taking it back again, sorry.
Hello, can you come again, please?
Yeah, I said we lost you for five
Maybe
ten
you may
seconds.
have to turn off your camera to maybe to add the boundaries a little bit
Yeah,
because
yeah, yeah. So
it's I'm
let me
getting you,
also
but
yeah,
it's
let me
interrupted.
also
Yeah,
off my camera. Yeah. So I was so
yeah.
can you hear me
Thank you.
now? Can you hear me?
Yes, that's better.
Yeah, I was saying
Yeah.
since the introduction kind of is important, we lost you for 5 10 seconds. So it I think it might be good if you take that again for us because Personal
Okay, you want me
evidence
to
of
go back
arrest.
again?
Yeah. Just that part with this device. I think the first part with the Mirai bot was fine, but that part, the next, we lost you a bit for 5-10 seconds, so it wasn't. Uh, so yeah,
Okay,
you have the floor again.
okay, no problem. So, you mean here on my screen?
No, here is fine. I think when you started, yeah, when you started the
Hello,
next,
just to
yeah,
confirm.
yeah, the
Do you
next,
mean here?
next. I think.
Okay. So actually here, come again, please.
Yeah, I said next. The Mirai bot I think was fine, but the next part. Hello. Did we lose you? Hello, Volviane. Hello. I think we lost Volviane again for. Hello. Hello. Um, Let me check on Volviane again. Um, okay, she's. Yeah, sorry. The internet is not with us today. Obviously, we'll wait for her for a few seconds. Probably she will be back. Let me check on her actually.
Damn, I'm back. This is serious today. So
Welcome,
sorry for
welcome
this.
back. We will make it. Hopefully.
Yeah, hopefully.
Yeah. Next. Yeah. Someone was saying next again. The next present.
Okay.
Yeah.
Here? Okay.
Next again. Next again.
Next we just have the outlier. So
No. Next where you had the. I said next.
the,
When you had the. Yeah. Exactly here. Here.
here.
I think it's here.
Okay.
The
Okay.
context. Yeah.
Okay, let me keep track on this stream because it seems like I'm going offline and I'm not even aware of it.
Okay. Okay.
Let me just put it here. Okay. So here I was actually just showing this Roku. This is actually called a Roku streaming device, and this device is actually used for streaming videos and on our TVs. And recently, this device were hit by a major attack. Recently, this is 2 or 3 months ago, and this shows us that IoT vulnerability are still a big issue. Since 2016 that we discovered the Mirai botnet, this has not been solved yet. So we are still having devices that are being attacked and causing very big issue to to users. And now, in the rush to bring product to the market, actually, manufacturer usually overlook security, resulting in vulnerability like easy guessable password that leaves device exposed. And also, many of us here have IoT devices, and also many of us do not even change those passwords when we buy our device. So, which is actually critical because this let us be very vulnerable. So IoT actually here in terms of background is just connect everyday object, like every object that can be connected together, embedded with sensor and software to exchange the data over the internet. So look at IoT device as everything that can be connected to exchange data. So while IoT actually enables smart connectivity, it faces challenges like context awareness, heterogeneity, mobility, scalability, and most critically, security risks such as hacking, weak encryption, and unauthorized data. And this is the part that we are going to look at today. So as IoT actually rapidly grow with over 75 billion devices expected to be connected by 2025, the need for robust security becomes critical. So already 48% of companies using IoT have faced breaches, highlighted the huge challenge in securing this device from cyber attacker. So a lot of people have been using IoT devices. Many of them are not aware of the vulnerability that they have. So there is a need for researchers to look at how do we propose a robust security measure for them. But the problem here is that the researchers are working on it, but the solution that they propose that we call here traditional method falls short usually because they are reactive instead of being passive. So leading to the need for innovative approach like cyber deception that we are going to talk about today and which is the central of this research. So with cyber deception, we use tactics like fake information, decoy, and misleading response to disrupt malicious activity, and let them think that their activity is being going through the network and not
Hi, Volviane. We lost you. So, hi.
am I still on?
Yeah, we lost you when you started saying, when you started talking about uh, the cyber deception, I think.
Yes. So, okay, thank you. So, I was saying the cyber deception tactics like decoy and misleading response are actually tools to disrupt malicious activity in such a way that when attackers make an activity or a malicious activity into the network, they think that the activity is actually going through while it's not. So basically, um this is what the cyber deception is, but we will go in deeper into it later. So with the rapid growth of IoT devices, existing security measures remain actually reactive, as I was saying, and can't keep up with the exponentially increased vulnerability because of the heterogeneity of IoT devices and also the fact that they are being growing very, very fast. So given this big issue, there is actually a need uh, for innovative and proactive strategy to protect IoT device from persistent and advanced threat. So what we want to tackle here basically is actually given that IoT there are already IoT security measures that exist, but those security measures are not able to capture a new type of attacks given the fact that IoT devices are being it's growing exponentially. So this fusion problem actually raises key research questions such as what are even the common vulnerability in IoT device and what is even a vulnerability? How are they exploited by attacker? And how can we design effective cyber deception techniques to mislead and capture those attacker? And finally, how can we make use of machine learning to detect threat and enhance the cyber deception in IoT? And we can also explore the impact of this approach in the IoT security network. So to answer this research question, the main objective of this research work was to develop a proactive security measure that scale with the growing number of IoT devices and also adapt to the evolving threat. Remember, we aim to create a comprehensive security framework integrating machine learning, and cyber deception to protect IoT devices from cyber attack. But to achieve this main objective, we will first of all look at how can we identify and analyze the common IoT vulnerabilities. What are the machine learning model that we can use or we can train to model and to detect the cyber threat, okay, that target IoT device. And we will also design and implement cyber deception techniques to mislead and capture attacker. And we will evaluate our system and see how it goes. So to implement our approach, we focus on cyber deception. And as I was saying in the beginning, cyber deception is actually a subset of cyber security strategy that create decoy, like what we call in cyber deception jargon, honey X. So this honey X is used to diverge the attacker. So it emphasize on defensive deception, which is contrast to attacker deception, where we use fake tools to mislead the attacker. So basically, the ultimate goal of cyber deception is to protect access or detect anything in the network that we want to protect. What we will do is we will create a fake things alongside the real one and expect the attacker to go for the fake one instead of the real one. So basically, this is what we are going to do here. But how do we do that? We make use of cyber machine learning. So alongside the cyber deception here, machine learning actually play a key role in our approach. And as we all know, machine learning is a branch of AI focused on building systems that learn and improve from experience. So machine learning, and it divides into many type of learning, such as supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. And in this research work, we more focus on reinforcement learning in order to adapt on the growing IoT device number. So with the rapid growth of IoT in the world today, key security measure like weak authentication. This is one of the vulnerability that we have, the weak authentication of IoT device, the limit encryption, and the privacy concern have been widely studied as highlighted by many of the author in the literature. So each layer in IoT architecture face unique trait, but in this research, we focus more on the attack that target the network and the middleware layers within the 5 layer of IoT architecture. So actually, author have focused on using machine learning to protect IoT device in many ways. So the first way is what we call the anomaly detection. And in anomaly detection, researchers develop model like support vector machine and k-nearest neighbor to detect unusual pattern. However, this model actually usually struggle with high dimensional IoT data and produce false positive, which was later on solved by using neural network of deep learning models. Next comes the intrusion detection, where researchers use decision tree and random forest to identify intrusion into the network. But despite the accuracy, they usually require frequent update to remain effective, as new attack pattern usually emerge, and also new device usually comes with new type of vulnerability, which makes the model more not always up to date to be used on the network. So another well explored security measure in IoT was the predictive analytic and the malware detection. And in this type, researchers usually use techniques like naive bias and neural network to detect intrusion into the network. While some authors focus on intrusion detection using technique like deep learning, the challenge here actually is the computational cost. Why? Because one of the property of IoT device that is that they do not have enough resources in terms of space. Like if you want to make a security measure for IoT device, you should make sure that it's less cost efficient. So it should not be like very large type of neural network that we usually train, and you should make sure that it's a light model. So, this study actually highlight both the potential and the limitation of machine learning in IoT security, setting actually the stage for more advanced actually produced by many other researchers online. But expanding on the role of cyber deception, what we call Honey X and more particularly Honeypot are the key tool designed to mimic real system, as I was explaining, and trick attacker. So they come in three types. The honeypot. We have the first type that we call the low interaction honeypot. So the low interaction honeypot here is actually the very simple system which that will just try to mimic the real system, but with a very limited, like it can be limited in terms of service or type of attack that they will mimic. And this actually have a very the main limitation, which is since they can only mimic a very restricted type of service or attack, they can also falls into the detection of an attacker. So an attacker can easily detect that this is a honeypot just by discussing with the honeypot, because the honeypot will not be able to reply in too much type of question, if like in diverse type of question, if the attacker asks them, and the attacker will be able to realize that okay, this is not a real system. So alongside the high interaction honeypot and the low interaction honeypot, we later on in 2010 have the high interaction honeypot. And when the high interaction honeypot, here is actually a real system that gather detailed information on advanced attack. And here the high interaction honeypot, take your IoT camera or your smart camera, for instance. You want to make a honeypot of that camera, the high interaction honeypot here will be buying another camera that will show something else than what an attacker can, like maybe than something else than maybe your home, if that is a surveillance camera, or have another type of false data that it's shared with the attacker instead of your real camera. But you can easily see here that the problem with this type of honeypot is that it's very costly and complex in terms of deployment, because you have to buy another real device, and it's also costly in terms of maintenance, because if you have problem on it, you have to call the technician as you have to call the technician for your real device, so which is actually not feasible at all. So in between the low interaction honeypot and the high interaction honeypot, we have what we call the medium interaction honeypot, which actually balance both and trying to offer a dynamic interaction with less complexity than the high interaction honeypot. So building on the limitation of the previous type of honeypot that I just cited, researchers in 2018 introduced a new level of interaction called intelligent interaction honeypot. And this type of honeypot using the interaction, but also actively engage them using machine learning to adapt and improve deception strategy based on the observed behavior during the conversation that they have with the attacker. How does this work actually? So the first type that was proposed was a machine learning model to learn how to reply to an attacker, like having like when the honeypot receive a question, or a request, whatever, it try as much as possible to reply as the real IoT device in order to diverse or to deceive the attacker. But the proposed intelligent interaction honeypot that exists now have a multiple limitation. The first one is actually the time of response. The first one took at least 2 weeks before it was able to reply effectively. That is, before 2 weeks, the model was just replying rubbish, like things that doesn't have sense. No, so this actually make the model make that type of honeypot before the 2 weeks more detectable by the attacker, which is not useful, because if you have to deploy such type of honeypot on your system before the 2 week, let's say before you reach the 2 week that your model will be responding appropriately, I think the most of the attacker will have been will have break down your system, and your security measure will not be useful anymore. So, in 2021, we have another research called Mukau, another type of intelligent interaction honeypot based on the sequence to sequence model. And here, the objective here was to train a sequence to sequence model that is able to reply to a specific response appropriately as the attacker wants. But the problem with this the sequence to sequence is that when the interaction goes like longer, the model start replying things like I don't know, or constant, or yeah, or fixed answer, which actually give the opportunity to the attacker to detect that, oh no, this is not a real device, because a real device never reply with fixed answer, or never replies with I don't know, like things like that. But this is what actually one of the limitation of the sequence to sequence model. But also the model wasn't able to capture, like it wasn't able to interact with the attacker until the honeypot is able to capture the real attack. So this actually shows the ongoing effort to create more adaptive and effective honeypot in IoT. But despite the advancement, key gaps remain in current cyber deception strategy. The first thing is that the static deception method lack real-time adaptability. When a like existing deception method are like, when they exist, they cannot adapt themselves with new type of vulnerability, new type of attack, or new type of data that comes later on, which is actually a problem, because device keep coming out every day, every time, with their vulnerability and so on, and user are not aware of those vulnerability. So we need something that will be adaptable. We also have the limit integration of machine learning with dynamic deception. Most of the work now have the only work actually have only implement the sequence to sequence model, and we all know that the sequence to sequence model is quite old, and we need something that will live under the sequence to sequence model, and that we can give us a very a better response to when it comes to dialogue, or when it comes to chatting. So, and we also have one of the limitation or the gap, which is a high interaction honeypot, in which face a very problem of scalability. You cannot have 100,000 of honeypot deploy at the same time when it comes with high interaction honeypot. So there is a need of having something that you can easily duplicate them and make them easy. So in IoT, usually in IoT attack life cycle, after sorry, after scanning the network, so this is how the scenario is. When an attacker scan the network, what happens is they actually do not know what is on the network. They will try to gather information about the target device before the launch what we call the exploit code. So if you have your sovereign's camera at home, or whatever, your smart watch or your smart refrigerator, and that someone wants to get access to it remotely, the person will not just let's say just enter your password and this and that, as you think, but the process will be scanning your whole network, yeah, being in the same network with you, scan the network, look at the vulnerability on the network. Here the vulnerability can be what are the ports that are open on your network, and once they find the port that are open on your network, they're trying to connect themselves to those ports. When they connect themselves to those ports, they will now try to gather information from the network that is hosting that port. So trying to gather information here is to build what we call the exploit code. And the exploit code is what they will send to your device in order to get access to your device remotely, like in order to get an unauthorized access to your device. So here, sorry. So here, what will happen is we need something that will be able to stand as your device at that stage. If we have security measure that will only stand as your device when let's say an attacker is already in your network, that doesn't make sense, because you cannot let your door open, wait for a thief to enter to your house before, I don't know, before you start saying that, oh yeah, I have someone in my house. The first thing will be trying to put a security guy at your door, try to lock your door, and so on. So here what we are trying to do is we want to put a honeypot that will be able to capture the attacker at the phase of scanning, like when they are scanning our network and trying to probe our device to get information to launch the exploit code, they will actually be talking to a honeypot instead of talking to our actual device. And the goal here is to build a honeypot that will be able to stand as an actual IoT device and reply like an IoT device. But there is one challenge. The challenge here is, okay, if an attacker send a request to the honeypot and the honeypot reply using whatever model, that sequence to sequence, or sorry, or any other type of model, how do we push the attacker to send a new request so that they will keep sending requests to us until they reach out at the time that they have to send the exploit code? So you see, here we have a challenge of choosing an appropriate response. Like, no, not choosing only the appropriate response, but also the expected response by the attacker. So you see here that the behavior and the preference of the attacker matters. And in order to choose this type of response, we first of all train our model. We train a model on a data set that we collected on emulated website. Just here the emulated website will just show us that this is how an IoT device will be replying to a specific request. And a request here can be a request of asking for a login page. To a request of asking a login page, many IoT device will reply with different response. An IoT device that have the login page will reply with the login page with the statue of 200 OK, meaning that yes, this is the login page. Another type of IoT device will reply with a response with a response status, sorry, with 404 page not found, meaning I do not have a login page, because there are devices that come with no login page. You cannot even log in, like the device is just there like this. And this is actually one type of response that the bot can have. Another one may reply with a 500 uh response, meaning unauthorized access, like you do not have the right to ask me for this type of page. And all these response, as you can see, to this specific request are valid response, but which one may be expected by the attacker in order to push them to send a new request? So this is the main question. So in order to solve that, what we do is, in our model, the model that handle the response selection here is called BERT. So um the bidirectional encoder from transformer here is draw from transformer, as you can see here. But though the transformer comes with the encoder and the decoder, BERT here has only the encoder. So the BERT was actually developed by Google in 2018, and BERT learns context from both direction. So that is from left to right and from right to left, making it highly effective in understanding and responding to variety requests. Okay, and yeah, so let us see deeper how BERT actually works. So before BERT process anything on the as a model, the input first of all goes through an input embedding. So this step actually convert word or token into dense vector of fixed size, allowing BERT to understand and process them effectively. So as you can see here, we divided the is considered to be the request sent by the attacker. We divide it into token that will pass into the input embedding. So after the input embedding, the output goes directly through the multi-head attention.
Hello. I think we lost Volviane for a few seconds again. Uh, let's see.
And here,
Hello.
the value matrix,
Hello.
the yes, yes,
Yeah.
can you still hear me?
Yeah. We lost you for when you started saying transformer. At some point, like when you started talking about the multi-head, I think at that point we lost you for 20 seconds or something like that. So if you don't mind taking it back a bit.
Yeah,
Hello. Yeah. Thank you.
yes, please. Yeah. Yeah, so I was saying that here the attention actually so after the input embedding, the output goes directly into the multi-head attention, and the attention here is calculated as the softmax of the scale dot product of the query q that you can see here and the key k matrices divided by the square root of the key dimension. So this step actually determines which token to focus on, and the value matrix here hold the relevant information for the input. Here the multi-head attention is simple the concatenation of multiple attention head. Like for each attention head, we just make the concatenation of all of them, allowing BERT to capture different aspects of the context of the input of the request input that the attacker sent. So after the multi-head attention, the output is passed through the linear layer, which is actually here used to flatten and then go through the softmax. And the softmax here, which convert the score into the probability in order to give us the 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 response that it's most appropriate. Sorry.
Hello, you are muted now.
Yeah, sorry. So I just wanted to grab a cup of water.
Okay, no problem, no problem.
Sorry. Okay, thank you. So, as I was saying, the response with um, with the highest probability here is returned as the output for the request. But there's a problem of privacy here because the response that we are sending to the attacker here are drawn from the real IoT device. So, because we collected those response from the real IoT device. That is, if an attacker takes time to collect all those response, he can go back, try to make a more powerful and send into the network. Because at the end of the day, the response that we send to him are real response, are response that an IoT device can send, which is actually a problem of privacy. But how can we solve this? How can we send a response to the attacker coming from the broad model, but which cannot be useful to the attacker? So to tackle this privacy risk problem, we introduce the adversarial setting that blur the response output by given by bird. So this actually ensure that even if the attacker gather information, it's less likely going to be not to be useful for further attack. Like, we want to give response that resemble as much as possible to the real response, but that cannot be useful. So here the generator actually learns from noise, aiming to mimic the real data. Like we try to we train a an adversarial, like we want to get an adversarial response. And but since the generator is coming from the noise, as you can see here, since the generator is coming from noise, meaning that the generator will just output rubbish at first. It's after some times that when the distributor, yes, the distributor will be penalizing the generator, that the generator will make better. But we don't want to take too much time before we are good. So we go from our transformer model, which is already our bird model, sorry, which has already the capability to respond very nicely or very good to the attacker. We combine the output of our transformer and the one of the generative model together and send it to the discriminator. Here, the discriminator will just have to penalize our fusion if the response seems to be too far from what the real response will be. And we propose three type of fusion method here. The fusion, the weighted sum between the output of the transformer and the generator, the simple concatenation, and the random selection. And later on, we will see that the weighted sum was actually the most effective. But there is a problem here. There is actually a problem here, because after this, we will surely have a response that is close to the real response. But how is this even different from the static method that we have seen on the literature review? Is this able to adapt itself with the growing number of IoT device? The response is no. Why? Because this model was actually trained on a very static data. If we have a new type of vulnerability tomorrow, this model will not be able to adapt on that type of vulnerability. If we have a new type of service or attack tomorrow, this data set will not be updated to or this model, the parameter of this model will not be updated to take care of that. So in order to solve that problem, what we introduce here is we introduce a reinforcement learning model that takes the top response that we fix as a given threshold, the top response of our GAN, and make go through the trying to make a kind of decision making to choose the response that we call here the expected response. This is the response that will push the attacker to send a new type of to send a new request. But not just that. This response will also be a type of response that if uh if we- if we have a new type of device that comes in, the model will not just choose the first or the response that give the high probability to be the one, but the model will go through and see which model has actually helped me to maximize my reward. Maximizing the reward here for a response is which response has pushed the attacker to send a new request. So how does this work? So this is done through what we call the epsilon grading strategy in reinforcement learning. So given the current state xt, which is our request here, the model either explore by randomly selecting the response yt with the probability epsilon, or exploit by choosing the best response based on the q-learning function with the probability of 1 minus epsilon. But and as I was saying, positive reward here will be the reward will be when the attacker send a new request after resending a new a response. And if we send a response and the attacker do not send any request, that means that response it was the appropriate response but not the expected one. And so for that request, or for that response, sorry, we will flag a negative reward. And this actually ensure that the model stay adaptable to new threat and doesn't stick to a fixed pattern. So to evaluate our model, we use the data set that we collected, and the data set was with more than 100,000 entries, and to train our model, and with the initial learning rate of 0.001, a batch size of 512. And after deploying the model, the most important part is how do we check the effectiveness of the response that our model is able to output. And in order to do that, we deploy our model on, we set up a simulation platform. Like we set up a simulation setting on Google Cloud platform for 20 days, and compare the result with existing model, like the one we presented on the literature review previously. So when you look at the learning curve here, it shows that the ground bird actually with the fusion, the weighted sum fusion actually outperform other fusion method in terms of accuracy, which shows that the weight fusion is better, because you can see how the random selection, this is randomly selecting between the output of bird and the output of the generated of the generator, or just making the concatenation of them, like the weighted fusion was outperforming that. And additionally, the GAN outperform the standalone bird, like just by using the only bird, you can see that the accuracy of the model of GAN and bird is also better. So after deploying, as I was saying, the most important part is to see the effectiveness of the deception here. So after deploying our model on Google Cloud Platform, what we did is we create a virtual machine on Google Cloud Platform with specific uh, vulnerability, such as we try to open some type of port, we can open the HTTP port, we can open the TCP port, like to make the server vulnerable. But more importantly, we put the IP address of the server public. Why did we do that? Because we actually need the attacker to scan and get access our our honeypot. But if you want your honeypot to be accessible, the IP address should be public. And also, the first 2 weeks of the deployment, sorry, what we did is we just deployed the model online, and we didn't specify, and while specifying the deployment zone to be Africa, the Africa zone. But after 2 weeks, what we got, we got only 2 requests to our honeypot. And we went back into the literature and we found out that there are specific zones where attacker usually where we have so many type of attacker, which is the first one is the Asia zone, the second one is the America, and the third one is Europe, and then Africa comes last. So we redeploy we redeploy our server on the Asia zone, and after 20 days, we were able to capture around 9,000 requests from over 1,000 IP addresses, significantly more than what we were able to capture with only the bird model and existing model in the literature. This actually shows that, first of all, our model is attractable. Like our honeypot here is attractable. It's attractive because if it means the way we deploy our model is more attractive than the way the others deploy theirs. So here, to see the effectiveness of the honeypot, we should see how long each attacker stay interacting with the honeypot. Because remember, the goal of training the model, making the model adaptable and so on, was to keep the attacker into deception as long as possible. So in order to measure that, we look at in the log file of the server, how many connection did we have. This is what we have just present here. And now, for each connection, how long does the attacker stay interacting with the honeypot? And we realize that more than 80% of the attacker stay interacting with the attacker for a session length of more than 7 minutes, which is very, very good because it outperformed the existing one, which was, if I can see, 11 or 15. Yeah. So this reduced the one of session length one. Session length one means an attacker will just come, connect with your device, or maybe connect with the open port, make one interaction, you give the response, not satisfied by the response, and give up. If we have uh, if we have more attackers that stay in session length one, the result will be our trained model or our intelligent model is not responsive. Like the way they respond is not good, because if they give the expected response to the attacker is supposed to send a new request, and that will that will make the session length large. But usually in cyber deception, measuring just the session length is not enough, because an attacker can be discussing with you and be saying rubbish. Someone can discuss with you 2, 3, 5 hours and not be saying something useful. So we need to look at what are the information that they are sharing during those 7 minutes. What are the information that they are sharing during those 1 minute of that they are interacting of interaction? So in order to measure that, we measure the volume of information that they are exchanging. Measuring the volume of information here will help us to see whether, if when the session length grow, the volume of the information grow as well. And this was the case, because you can see here that for the range at the box plot, for the range of information sent at session length 1, you can see that the maximum is very small, while at session length more than 7, it's very large. It means the more the attacker interact with the device, the honeypot, the more specific the attacker becomes, which is reasonable because the more specific the attacker become, the higher the volume of the information will be. Additionally, we were able to capture existing attack like DDoS attack, like local to route to local attack, like those that want to connect to your device and so on. And we realized that here in blue, you can see that our model were able to capture very well known attack compared to other existing model. So this actually shows that our gang and bird model effectively detect vulnerability and achieve actually the goal that we fixed in the beginning, which was detecting the common vulnerability in IoT device. But more importantly, we were able to also deceive the attacker. Why? Because we were able to capture the attack at the end. If we're able to capture the attack at the end, that means during the interaction, the attacker trusts our honeypot as much as possible, and this also means that the machine learning model behind were able to predict the most expected response
Hello. Um, Hi, Volviane. We lost her for just the last final sentence. We'll wait before we can take questions. I think our talk is um, I think it's over. So please, in the comments, if you have questions, please feel free to write your questions while we wait for Volvian to reconnect uh, or to come back online. Uh, Feel free. Then I will let me check on her. Okay, I think she will be back. Let me just come back online just to make it. Uh, yeah, it's actually a very nice presentation. Really enjoyed it. It's a very relevant topic. Um Using uh, uh, advanced model to detect or to protect IoT networks. So yeah, feel free. If you have questions, yeah, write them while we wait for. Yeah, I can imagine. Uh, yeah, you can write in French. It's no problem. I think you can write your questions in French. Um, uh, Please feel free to write in French. I can. I'll either. I think Volviane speaks French as well, so she can either respond in French or she will respond in English. I think it will be uh, her choice. I think but feel free to write your questions in French, please. Okay, she's back. Um, Hello. Hmm, Volviane. Let me check on her. Okay. Hello, hello. She said she cannot hear me. Let me tell her. Oh, she's locked out again. Yeah, already getting questions from Idris already in the chat. Um, yeah. Mm, questions. So meanwhile, Idris says, congratulations on the brilliant presentation. Given the memory issues in IoT devices, how do you manage the deployment on chatbots, honeypots on these devices? Actually, that's a great question because I was wondering, like, is it because the main feature of IoT devices is that they are low resource devices. So in terms of energy consumption or energy supply and memory or compute power, they are very, I mean, they are kept to the minimum. So yeah, I'm wondering how it is deployed. So that's the very relevant question. She had an architecture that explains how she deploys this. So let's wait for her. Maybe she has. I think she will give us the. She'll clarify that. Um, yeah, let's wait. She's still not back. Let me check on her. Yeah. Unfortunately, she doesn't have control over the internet supply, um, which is actually which is not. It's actually annoying. Yeah. Yeah. On another question from Tafo. Une première ambiguïté. On protège les devices, les users et les serveurs. Okay. What are we protecting? Devices, users, servers? Yeah. Uh, can you specify your question? Because it feels like, because I think the Internet of Things is about a network of devices. So it's basically a network of devices or things, as it says. So users, uh, or at least human users, are not directly involved. So I think it's so maybe I don't know if that's your question, but um, I think the internet the the network she's dealing with here doesn't involve of course indirectly we probably, I'm just guessing, indirectly she protects you protect users by protecting the but indirectly only, I think. But yeah, let's wait for her, please. Thank you for the patience, and yeah, she's trying. uh, uh, so she says in the night her connection is really bad in the night. uh, yeah, that's actually um, not um, not great. um, Idriss, à la slide 17, c'est possible d'expliquer les types d'attaques, définir et spécifier l'attaque réellement. Okay. I don't even remember that slide. Yeah, I think um, Mm, that would that would be cool because I think the presentation uh, was heavy in information, a lot of information. If you're not in the cybersecurity domain, obviously, or if you're new to machine learning, it might have been a lot of information. So coming back to explain certain things would be great. I see she's trying to come back. Hello, Volviane. Hello, hello. I can hear sounds in the background. So are you back?
Hello, can you hear me?
Yeah, we can hear you now. Great. So
Hello.
yeah, hello. Can you hear me? I can hear you. Hello, 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 hello. Oh, let's try. I hope you'll bear with me. Um, it's yeah. Yeah, Idriss says, en fait, la question de l'objet sécurisé peut vraiment m'aider à comprendre est-ce le device ou l'utilisateur? Oui, je suis d'accord. Oui, Volviane, je pense qu'elle va apporter la clarification. She will bring the clarification. Euh, Malheureusement, sa connexion Internet est terrible ce soir. Euh, euh, Merci de patienter. Thank you for patience. Um, yeah, keep the questions coming. Meanwhile, thank you, Idris. I will. I'll show them. Maybe. Yeah. Maybe I show the. Uh, Let me check. Okay. Wait. She's. Hello. Hello. Let me off my camera. Also, maybe that will help. Hello. Hello.
Yes,
Volviane.
I can hear you now. Okay.
Oh, great, great, great. Yeah, probably
Yeah.
my camera was taking some bandwidth too. So yeah, so we have actually a lot of questions from from Idris and probably coming more. Thank you for the presentation. Just to show you, I don't know if you can see the slide. It just says very, very good presentation. Uh, and he says he have a lot of questions and he will he would like to them in French, so he wrote them in French. So I don't know if he had some questions. So I don't know
Yes,
if
please.
you answer in French or in English. It depends on you. I don't know. So I will
Yeah,
share
whatever
them.
language. Okay.
Yeah. So yeah, congratulations on this brilliant presentation. Given the memory issues in IoT devices, how do you manage the deployment of chatbots or honeypots on these devices? That's the first question.
Okay. So thank you so much, Idris, for the question. Uh, is this the question I should answer in French?
No, no, no. Answer in. I mean, I guess you will have. I think this since no, there are two Idris. Actually, I realized there are two Idris in the chat. The one that says he will
Okay,
ask.
there are two. Okay,
Not
there are
yeah,
two
yeah.
Idris.
So you can answer. Yeah, in English. If you. Yeah.
Okay. Thank you. So, first of all, Idris, I want to just to mention that the honeypot is not deployed on the device. The honeypot is deployed alongside the device. Like you have your honeypot and you have a virtual server somewhere that has a model that is able to reply as an IoT device. This is why, because given the size of the model, you cannot deploy it on the IoT device because of the resource constraint of the IoT device. So what we did is
Oh. Um. We lost her again. Yeah, a bit of patience. Yeah, I'm just telling her we lost her right now. Don't know if she's. Yeah. Yeah, I think what she was about to say that the model is it's not deployed on the it's not deployed on the IoT devices. I think it's deployed somewhere uh, in front. So yeah, let's wait. Let's wait again. Hmm. Okay, let me check on her coming back. Yeah, I was saying we have no choice but wait. Uh, I'm sure you faced those kind of internet problems. Uh,
oh
um,
sorry guys, me I'm facing this crazy problem today. I don't know why.
yeah, yeah,
So
no problem. Yeah, go ahead.
can you can you still hear me?
Yeah, yeah, we can hear you now clearly. You can continue your response.
Okay. Uh, is the question clear?
Yeah, I don't know if Idris, is it clear? Have you? Is it okay? Yeah, I think you had an architecture. Hello. You had the
Yes,
architecture at some point that shows where the bird is deployed, which is not directly on the IoT devices, right?
exactly.
Yeah, yeah. Okay. Idris says, okay, let's go to the next question. Euh, Now it's Idriss Tafo in French. Une fois de plus, merci pour la présentation. Une première ambiguïté. On protège les devices, les users ou les serveurs? C'est la question.
Ok. Merci Idriss pour ta question. Donc, et désolé pour l'ambiguïté. Donc déjà ici, on veut protéger les devices. Donc, on veut protéger l'objet et par transition l'utilisateur. Donc, l'utilisateur utilise l'objet. Les informations personnelles de l'utilisateur sont dans l'objet. Donc, d'une part, on veut également protéger en premier, l'objet premier ici qu'on veut protéger, c'est le device parce que c'est lui qui est en contact avec l'attaquant.
Right, 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 right. right? Oui, allô?
Oui.
Oui, oui, je pense que ça clarifie la question, je pense. Oui. Euh, euh, Tafo, est-ce que c'est clair? Je passe à la prochaine question euh, avant que avant que Internet ne nous quitte, before Internet leaves us. So, à la slide 17, c'est possible d'expliciter les types d'attaques, définir et spécifier l'attaque réellement. Slide 17, je ne sais pas, est-ce que tu peux nous remontrer les
Okay.
slides? Can you show us the slides again? So just to translate the question, he asked, um, is it possible to show, I mean, for those who are connected that are not bilingual, so is it possible to explicit the types of attacks? Let me add it to the same and
Okay.
define each attack and réellement. Yeah.
Actually here we wasn't in this slide. This is slide 17. Yeah. Donc, pardon, je vais aller en français.
Ouais,
Donc, Idriss, ici, ce qu'on essayait de faire, c'était de faire une revue de littérature globale des techniques qui ont déjà été utilisées, qui ont déjà utilisé le machine learning, voilà, pour protéger l'Internet des objets. Donc, en termes d'attaque spécifique, ce que nous taguons ici comme attaque spécifique, ici, c'est l'attaque par reconnaissance que j'ai expliqué ici, de ce côté-ci. Donc, ceux-ci, avant, dans la littérature, s'intéressaient aux attaques après cette phase ici là. Donc, la phase, donc après, passer dans le cycle d'attaque d'Internet des objets, ce qui se passe d'abord, c'est qu'il y a le scan, il y a la phase de scan. Après la phase de scan, il y a ce qu'on appelle la phase de probe. Donc, l'attaquant essaye de prober ou bien essaye de discuter, si on peut dire ça simplement comme ça, de discuter avec l'objet pour avoir plus d'informations sur l'objet. Et donc, cela permettra donc à l'attaquant de fabriquer le code d'exploit, c'est-à-dire le code d'attaque. Généralement, les solutions proposées se placent à ce niveau-ci, quand le code d'attaque est déjà là. Ces solutions-ci que vous voyez là, telles que les détections d'anomalies, les détections d'intrusions, les détections de malware et tout, ce sont des solutions qui se placent, qui sont utilisées quand l'attaque a déjà eu lieu. Mais nous proposons ici quelque chose qui va attraper l'attaque avant que l'attaque n'ait lieu. Donc, quelque chose de proactif et non de réactif. Je ne sais pas si ça clarifie un peu.
Ouais, à Idriss de réagir. Idriss, can you react if, anyways, you can ask subsequent question if in the chat if it's not clear. Donc, Idriss, tu peux ajouter des questions supplémentaires si ce n'est pas clair ta question. Donc, je vais continuer. I will continue with the questions. So Idris again. So that is about which object was protected. I think you answered that. Next questions. À la slide 18, rate limitations peut être une solution, surtout si on parle de l'hypothèse que les devices consomment une ressource commune, API et autres. Volviane, est-ce que tu peux voir la question que je...
Oui, je peux voir.
Oui, ok, oui. Donc, tu as la question. Oui.
D'accord. C'est vrai que la question, je n'arrive pas à la comprendre exactement. Slide 18 peut être une solution. Peut-être une solution, surtout si on part de l'hypothèse que...
Yeah, I think I will invite him to clarify his questions.
Yeah.
And then we move to his next question.
Slide 19.
Slide 19. Tell me if you understand that one.
Ok, émuler tout. Les différents types de devices est vraiment impossible et donc ne peut pas être une solution fiable. Oui, en effet, Idriss, justement, émuler tous les types de devices sont bon. En recherche, généralement, je préfère ne pas utiliser le mot impossible parce que là, avec l'utilisation du reinforcement learning qu'on a appliqué ici, on veut donc rendre ça possible. C'est-à-dire que avec, puisque on ne sait pas, on n'a pas tous les comportements des devices, on n'a pas tous les comportements des types d'objets, on n'a pas tous les objets, mais ce qu'on voudrait, c'est réagir au fur et à mesure que on constate quelque chose sur le comportement de l'attaquant. Donc, si on se rend compte, par exemple, que l'attaquant est plus, je vais dire, est plus attiré par quelque chose de spécifique, on réagit de façon spécifique et donc on comprend qu'il y a quelque chose de nouveau sur la toile. Et quelque chose qui rend notre système, si je peux retourner dans mes slides, plus adaptatif, c'est ça. Donc, quand on reçoit une requête, quand la requête est envoyée, on a notre base de données initiale. Dans la base de données initiale, on a les requêtes qui sont composées, les requêtes de tout ce qu'on peut connaître, de tous les types de devices qu'on a et tout. Mais non, s'il s'avère que c'est une requête nouvelle, c'est une nouvelle requête qu'on n'a jamais vue, et donc, nous considérons ça comme un out of vocabulary request. Et ce qu'on fait, c'est qu'on voudrait quand même avoir des réponses par rapport à cette requête. Et donc, on essaye de collecter les informations par rapport à cette requête sur Internet parce que sur Internet, il y a les devices qui ont généralement certaines vulnérabilités et qui donnent la possibilité, qui répondent aux requêtes. Donc, nous-mêmes, on envoie cette requête-là sur Internet. Bon, c'est éthiquement pas très correct, mais ça se fait parce que beaucoup de recherches l'ont fait. On envoie là et on collecte. Ceci permet que si à jamais il y a un type d'objet qui est apparu entre-temps et qui n'était pas dans notre base de données, juste par cette action-ci, on collecte les informations par rapport à ce type. Et c'est pour ça que nous avons nommé ceci Adaptive Intelligent Interaction Honeypot. Parce qu'en plus de s'adapter avec l'évolution du nombre de devices et des types de devices, il s'adapte, il est également intelligent et répond de façon appropriée et de façon appropriée à l'attaquant. Je ne sais pas si ça clarifie ceci au slide 9.
Oui, oui. Je pense qu'il dit merci pour les réponses. Je pense que oui. Euh, oui, je ne sais pas si la dernière question, if the last question, the question that he asked last comes first now. I don't know, but I will just continue with the chronological order they came in. Then we'll see. Next is slide suite 22. Wait. You can see it now on screen.
Ok. Quand est-il si on stream la donnée avec le protocole de caméra surveillance, par exemple? Qu'en est-il? Ok, d'accord. Ok, merci beaucoup, Idris, pour ta question. Slide 22. Ok. Pardon. Ah oui, d'accord, il y a des petits problèmes avec les slides. Sorry. Ok, le numéro des slides. Donc, je suppose que c'est quelque part ici. Ouais, ça doit être quelque part ici. Donc, normalement, ici, le code d'attaque ici que l'on veut détecter, c'est l'objectif de ce papier s'arrêtait à ce niveau. Du moment où on a pu attraper le code d'attaque, on s'arrête là. Mais ta question est assez pertinente parce que on s'est également posé la même question. Maintenant, si un attaquant, après avoir envoyé le code d'attaque, veut avoir quelque chose de plus juteux, comme par exemple une vidéo, Par exemple, il veut avoir accès à une caméra de surveillance. Quand on a accès à une caméra de surveillance, vidéo, on est censé voir voilà. Qu'est-ce qu'on fait? Et donc, on a proposé une autre technique dans un autre travail qui permet de garder l'attaquant en déception en lui proposant des vidéos déceptives. Donc, peut-être on aura l'occasion d'explorer cela une autre fois dans une autre présentation ici. Mais ce travail-ci ne tient pas compte de ça. Donc, une fois qu'on a détecté que voilà, il veut comme ça lancer une attaque pour avoir accès à la caméra de surveillance, voilà, le travail l'objectif de ce travail est atteint.
Okay. Okay.
Mhm.
Je pense que ça répond à la question. I think it answered the question. Basically, you have not yet yeah, dealt with that kind of protocol. Another interesting question from Idris says, uh, basically, GAN architectures are difficult to train. How do you can you explain the combo between these two? Est-ce que tu peux expliquer
Ok,
oui, la question?
d'accord. Ok, merci beaucoup Itis pour tes brillantes questions. Donc, tu as parfaitement raison avec le problème de convergence de gain. Donc, tu vas constater ici que l'on a décidé de faire une fusion. L'idée de faire cette fusion-ci, justement, c'était pour, en quelque sorte, éviter ce problème de convergence des modèles de gain. Donc, cette fusion nous aide à nous rapprocher le plus vite possible de la bonne réponse, si on peut dire ça comme ça. Donc, le transform Albert nous déjà connaît comment on répond à la réponse, à la question. Mais, sauf que nous ne voulons pas qu'on réponde de cette façon-là. Mais on veut répondre d'une façon plus proche de cette façon. Et donc, on fait la fusion entre ce qui ne converge pas et ce qui converge déjà. Sachant qu'en faisant la fusion, d'une façon ou d'une autre, le gain va finir par converger. Peut-être pas à peut-être à un local optimum, mais il va finir par converger. Et puisque le transform, lui, il converge déjà, on fait la fusion. Et vous allez constater que on a proposé 3 types de fusion. Et avec les résultats qu'on a obtenus, on s'est rendu compte que la fusion de la somme, je ne sais pas comment on l'appelle, le weighted sum, était la meilleure. Pourquoi? Parce que ça nous permettait de balancer, de faire une sorte de balance. Donc, quand on a commencé l'entraînement, Neta était à 0. Donc, Neta va de 0 à 1. Quand Neta est à 0, ça veut dire quoi? Ça veut dire qu'on ne tient même pas compte du output du gain, puisqu'on sait que de toutes les façons, dans les premières itérations, le gain ne converge pas. Il ne donne même pas des réponses qui ressemblent à quelque chose. Et donc, on tient compte que de ce que le transform donne. Mais au fur et à mesure qu'on entraîne le modèle et que le discriminator est en train de pénaliser le generator, alors on tient compte au fur et à mesure d'une quantité appropriée du output du generator. Et c'est ça qui nous permet de rester dans une convergence acceptable parce que d'une façon ou d'une autre, le GAN nous pousse, le BERT, pardon, nous pousse plus vers la convergence que le generator nous éloigne ou bien nous diverge vers là grâce au weighted sum que l'on a utilisé pour la fusion. Je sais pas si ça répond à la question.
Oui, probablement. Et juste pour compléter sur ça, or in English, so what value of eta is do you use that works better? Is it close to 0 or close to 1 or half is the best?
Yeah, exactly. Somewhere in the middle.
Okay.
Yeah,
Okay.
because when it's 0, it means we are using all the output that we are using here
Only
is
from
just the
the
one from birth.
birth and the yeah. Sure.
And when it's close to 1, or when it's even 1, it means we are using only the one from the generator. Like
Okay.
the one that balanced between both was the one that gave us the right
Okay.
output.
Okay. Okay. Next question. Wait. Um. Yeah. I think it's a series of questions in the same line. So yeah.
Okay, so I have a question here. So avant l'attaque, I don't get this.
Yeah. It was
Supposons,
complementary to something. I don't know. Let me show you the last he put. I don't know if it's related. But um. Can you?
okay. Yeah, I get Idris' question.
Yeah.
Idris, juste pour vous mettre dans le contexte, ici, comme je le disais encore, ici, l'attaquant n'est pas encore dans le réseau. Donc, je prends un scénario. Il y a quelqu'un, vous avez votre maison, vous avez votre barrière, et puis, il y a quelqu'un qui essaye bon, non, je vais prendre un autre scénario plus simple. Donc, on est dans un système de l'hôpital, par exemple, où on a le système qui mesure la tension du patient. On a le téléphone de l'infirmière. On a l'alarme. Voilà peut-être les trois devices qu'on a, qui sont connectés et qui communiquent ensemble. Si la tension du malade, du patient augmente, mais si ça atteint une certaine valeur, l'alarme est censée être déclenchée. Et donc, l'infirmière est censée réaliser cela sur son téléphone et donc courir vers le patient. Ce
Mhm.
qui se passe, c'est que ces objets-là sont connectés à l'hôpital, je ne sais pas, l'hôpital d'où, peut-être l'hôpital de Dschang, disons ça comme ça. Et donc, il y a Idriss qui passe par là. Il scanne en utilisant l'outil, je vais dire quel outil par exemple, Nmap. Idriss a l'outil Nmap et il l'utilise pour scanner le réseau de l'hôpital, le district de Dschang. Et il observe que il y a certains outils, ou bien il y a certains objets du réseau de l'hôpital qui ont des ports ouverts. Je prends juste cet exemple. Ces objets ont des ports ouverts, mais Idriss n'a aucune idée de ce qui peut être caché derrière ces ports. Ok, il y a peut-être des ports ouverts, des protocoles que Idriss connaît. Ok, il veut explorer pour savoir s'il peut avoir accès à ces objets-là, aux objets de ce réseau. Rappelons, Idriss n'est pas encore dans le réseau. Idriss n'est pas dans le réseau, donc on ne peut pas parler de paquet ici. Les éléments du réseau sont en train de s'échanger des informations, mais Idriss n'a pas accès parce que Idriss n'est pas un membre du réseau. Donc, on ne peut pas parler de paquet ici. Bon, nous, maintenant, ce qu'on veut faire, c'est que on veut empêcher à Idriss de collecter les informations par rapport au tensiomètre du patient. Parce que si Idriss parvient à utiliser le port qu'il a vu ouvert avec son outil Mmap pour collecter les informations, c'est-à-dire connaître quelle est la version du firmware, ça c'est de l'intergiciel, voilà, que le tensiomètre utilise, quelle est la version. Et donc, de là, Idriss peut connaître quelles sont les vulnérabilités, quel est le mode de passe par défaut et tout, jusqu'à ce que Idriss puisse lancer un code qu'on appelle ici le code d'attaque, qui sera peut-être le code pour augmenter la tension du patient. Ceci peut-être dans le but de faire sonner l'alarme et de faire courir l'infirmière vers le patient et d'opérer peut-être dans la salle où l'infirmière était. Ou bien d'aller là-bas voir quelqu'un alors qu'il n'avait pas accès. Vous voyez un peu? Donc, maintenant, ce qu'on fait ici, c'est qu'on veut empêcher à Idriss d'avoir accès au tensiomètre. Et donc, on place quelque chose à côté dans le réseau que le tensiomètre. Idriss, lui, va scanner le réseau, tomber sur notre objet, entre guillemets, qui est attractif, essayer de collecter les informations, pensant qu'il est en train de collecter les informations du tensiomètre, notre honeypot va répondre comme si il était le tensiomètre, ok? Et une fois que Idriss va envoyer maintenant le code pour augmenter l'attention, l'objectif sera atteint. Que là, premièrement, on apprend qu'il y a les gens autour de l'hôpital de 17 ans qui voudraient augmenter l'attention pour une raison qu'on ignore des patients. On apprend que le tensiomètre a une vulnérabilité, vous voyez, au fur et à mesure. Et on apprend un certain nombre de comportements sur les attaquants qui peuvent. Et revient donc ceci revient à l'administrateur.
Uh, I was suspecting that it was getting bad. Yeah, she disconnected. I think yeah. Hopefully hopefully you said Idris said this answers his questions. Uh, yeah. Yeah, yeah. D'où l'intérêt du honeypot en entrée. Yeah, great presentation. We'll we'll wait for her just to conclude. Okay, she's back. She's back.
Allô?
Oui, allô.
Ah,
On t'appelle. Oui, c'est bon, c'est bon. Oui, je pense que Idriss a dit. Bon, il a dit. Oh, je vois. Je pense. Tu vois maintenant le. Tu vois.
ouais, je
Tu vois.
vois. Oui.
Oui, il dit c'est clair. C'est trop clair même.
Ok.
Interesting
Ok.
one. Et
Ok.
yeah, il a d'autres commentaires. Je sais pas si toi tu vois le chat quand même.
Oui, je vois.
Oui, je peux voir. Et il y a une dernière, enfin pas la dernière, mais il y a une question aussi qu'il a ajoutée là avant. C'était sur le rack versus le BERT. Tu peux lire la question. Donc, il dit sur l'architecture, je remarque que BERT est juste un générateur de réponses avec une base de connaissances spécifique, database. Question. Un rack avec une base de données vectorielle n'est pas plus. C'était quoi le. N'est pas plus. N'est pas plus quoi?
Bon, n'est
Euh,
pas plus. Je peux juste arrêter
Peut-être
là.
plus intéressant, je ne sais pas bien. Bon, est-ce que tu as quelque chose à dire par rapport à ça?
Oui, peut-être, Idriss, ça pourrait être intéressant. Je crois que il faudra implémenter et expérimenter pour voir ce qu'on n'a pas essayé. Donc, je crois que c'est une piste à explorer également. Merci.
Okay. Oh, we have some Salvador Fernando who asked, brilliant presentation. What challenges do you foresee in implementing the proposed model in real-world IoT networks, and how adaptable is it across industries with different security standards? Yeah.
All right. Thank you so much, Salvador, for joining and for asking the question. So, as this is actually a very tricky question, by the way. So, this being a research and being simulated, it can surely be applied in real world network, IoT network. But then we have to be we have to be we have to very carefully think about making the difference between the attacker and the legitimate user, because even the administrator system usually scan the network. So it can happen that the administrator system get into the honeypot and being deceived, which comes with the ethical issue. But this is actually something that can be implemented in the real world situation when comes with very when comes with something like smart home. But if we go into big IoT for industry, we will have to make some type of adjustment, because the data set on which we train this model wasn't have did not take into account those type of IoT that are used on the industry. This was just with smart home, like smart device that we have on our home, and yeah. So in order to for this um to be implemented in the industry, we need some to adapt the data set first of all. I don't know if
Okay.
this answered the question.
Okay. I think Salvador will react. While waiting, ab- about this real world. So I had a question about how you evaluate that. Actually, you were talking about what you that you were saying that you deployed something on the Google Cloud platform, and I was wondering if you deploy something and just wait that you get attacks, or how did you actually evaluate that? I didn't get that part correctly. How you evaluate your system?
Yes. Yeah, so usually how this is evaluated is you have your physical server, like you have a server with a
Mm-hmm.
public IP address. You
Mm-hmm.
deploy your model on it, and you maybe look for people to whom you share the IP the IP address for them to try to probe your system. But due to resource constraint in terms of first of all the server and the human that will be doing that, like the human with the attacker expert that will be doing that, what we did is we create a virtual machine on Google Cloud platform with an IP address make public
Mm-hmm.
on the zone that it's this declare like zone where we have a lot of attacks, which is the Asia zone. Okay, so after you've done that, you just cross your fingers and you wait for them to probe your system. But it
Okay.
actually works because just in 20 days we were able to get the result that let us know that this is actually effective. Because trust me, they will try to probe your system every second. But if you deploy it in Africa, no, don't expect anything, because after 2 weeks I had only two probe on my system.
Okay. Okay.
Mhm.
I guess like just to yeah, I get it. I get it now. But just for clarifying, probably when you deploy in Africa zone is not that big. Maybe it not only that maybe they are not Africans attacking it, but maybe probably people think that there is nothing to protect there or something like that. So maybe that's why people attack less when it's deployed in these zones. Maybe. Uh,
Yeah, maybe because
okay.
I find a research that was sharing something very interesting that we uh, because when you deploy with public IP address in Africa, it means people in Africa can see it more easily. Okay,
Okay.
if they
Okay. Okay.
scan
Okay. Okay. Okay.
the system, they can see it more easily than those in the other than those in the
Okay.
other zones. So,
Okay.
and
All
the
right.
research was saying that people make much prop in those other zones that in Africa.
Okay.
Mm.
Okay. Yeah. Salvador said yes. You answered his question. Um, I don't know if there are other questions. It's really a very interactive session. Um, also, yeah, maybe while seeing if someone will ask another question, maybe I'll ask maybe one last question. So, the IoT, it's a network of devices which are supposed to uh, uh, communicate. So I was wondering, the device that communicates, how do you distinguish the a request that comes from a legit device? Because if you are replying to the attacker with some deceptive replies, this could also be given to another device. How do you distinguish if it's a legit device or a legit request or some attacker trying to hack in?
Okay, so this was just we made an assumption. The
Okay.
assumption was if we have usually the administrator system is the one setting the defensive security measure, okay? So if you put something as honeypot and you connect on it by yourself, that means there's something that is wrong with you, right? And the administrator system is the one that can scan the network, so he is the legitimate one.
Okay, okay,
Every other person apart him,
okay, okay,
we
okay, okay,
consider it as
okay,
a
okay.
honeypot, as
Makes sense.
an attacker. Yes.
Okay, makes sense, makes sense, makes sense. Yeah, it just was just reacting to my pseudo question. He was just saying that there are not a lot of servers in Africa also. Yeah,
Okay.
just clarification. Uh, we've been it's been a long one. Let's just
Yeah.
see if people still react. Um, at least the internet was troublesome, but we made it through.
Yeah. Thank you so much. I'm so sorry. Sorry for this. So
No,
the
it's not your
internet
fault.
invite himself for today. So, so sorry. And hope
Yeah,
next time will be good. Yeah.
it's not your fault.
Okay.
I've faced that. I totally understand. It's it's real chaos. Yeah.
Thank you.
Let's see. Okay, a few more seconds if someone will react. Yeah, it was a great presentation overall. I don't know if you've seen the reactions. It's like, oh, they really loved it. I personally enjoyed
Yeah.
it.
Thank you.
Uh,
Thank you.
it was very instructive. Yeah, Idris Tafo again. Let me put his question up. Euh, Juste une question. Si le honeypot a déjà simulé la réponse, pourquoi l'attaquant doit encore traîner? Uh, I don't know if you understand the
Traîner.
question.
Non, traîner pourquoi? Oh my God,
Idris, can
please.
you add the precision to your question? Qu'est-ce que tu peux préciser ta question? Ah, yeah, yeah, I understand. Like, if, for instance, I think, je pense qu'il dit, si le honeypot donne déjà une réponse, qu'est-ce qui fait que l'attaquant reste plus longtemps s'il a déjà reçu une réponse? Qu'est-ce qui le fait rester? Parce que tu mesurais aussi le temps que ça prend pour que l'attaquant reste sur
Oui,
place.
ok.
Oui, allez.
D'accord, je vois. Oui. Donc, du coup, ce qu'on regarde ici, c'est que n'oublions pas qu'on est dans une phase de probing. Donc, l'attaquant est en train de collecter les informations. OK? Donc, il collecte les informations. Et quand, par exemple, tu fais une conversation avec quelqu'un et que tu veux avoir une information, ce que tu fais, c'est que à chaque fois, tant que tu n'as pas l'information, tu ne t'arrêtes pas, n'est-ce pas? Et l'information qu'on veut ici, c'est l'attaque. C'est le code de l'attaque, là. Quand tu dis bonjour, bon, si tu réponds bonjour, c'est tout, la conversation s'arrête. Bon, mais si tu dis bonjour, comment tu vas, ça pousse la personne à envoyer une autre réponse. Ok. Bon, si je te demande, si l'attaquant te connecte et dit, OK, quel est l'interlogiciel que tu utilises, l'interlogiciel, sans donner la version, automatiquement, c'est que l'attaquant va envoyer, OK, va également envoyer quelle version interlogiciel là, c'est quelle version. C'est ça qui va pousser la conversation un peu plus longue jusqu'à obtenir le code d'attaque. Si le statut que je parlais de tout OK, c'est juste pour montrer que voilà, je comprends ta question. Ça, c'est pour les requêtes HTTP où la requête est acceptée. Donc, c'est une requête qui aura une réponse OK. Donc, c'est le statut pour dire que voilà, ça marche, je t'envoie l'information que tu veux ou pas. Il y a tout OK pour dire que voilà, je t'envoie la réponse. Il y a 4.
Oops. Yeah. Yeah. Mhm. Yeah.
Hello?
Welcome back. Yeah. I think after that we will close, but yeah,
Yeah.
continue. Yeah. Yeah. Go ahead.
Oui, donc du coup, je crois que j'avais terminé.
Ok, ok,
Je sais
ok.
pas si la
Oui. Oui, il a juste fait la commentaire, oui. Je pense que, oui.
réponse est claire. Oui,
Oui, il a ajouté quand je scrape un device, je sais déjà ce que je veux. Et comme c'est l'automatisation, j'aurais. Requête est une très. Ah, ok. Ok, je veux juste un truc précis. Si le serveur répond. Voilà, il dit si le. En fait, justement, comme tout à l'heure, je pense, si je comprends bien sa question, c'est si par exemple je viens, parce que je voulais savoir la version du, du firmware qui est sur le device, par exemple, est-ce que si je demande et qu'on me répond, normalement, j'ai atteint mon objectif, tu vois? Qu'est-ce qui permet, qu'est-ce que tu fais pour garder la conversation ou bien, en fait, je pense que c'est dans ce scénario-là qu'il se place parce qu'il dit, dans ce cas-là, la discussion est terminée puisque je voulais la version de firmware, tu me
bon,
donnes. Est-ce que...
si l'attaquant a fini par envoyer le code d'attaque, est-ce que, bon, la question c'est à toi, en tant qu'attaquant,
oui.
d'envoyer le code d'attaque? Si oui, tu envoies le code d'attaque.
Ok, justement, il envoie le code d'attaque. Je suppose que normalement, ça va échouer
Information
puisqu'on lui a donné...
suffisante.
Oui. Allô?
Oui.
Je suppose que dès qu'il a sa réponse, il envoie le code d'attaque et ensuite, si ça échoue, il continue. Ça va échouer puisqu'on lui a donné fausses informations, mais il reste pour demander plus d'informations. C'est ça qui traîne, c'est ça qui donne c'est ça qui rallonge le temps, euh, son temps son temps de communication avec le device ou bien qu'est-ce qui...
Non, non, pas vraiment. En fait,
Hmm.
il demande la version, par exemple, il demande le firmware, on lui dit. Il demande la version du firmware, on lui dit. Mais la question, c'est est-ce que ces informations-là sont suffisantes pour,
Ah, ok.
pour
Ah, ok.
monter le code d'attaque?
Ok.
Si oui, il monte le code d'attaque et il envoie. Mais l'avantage ici que vous devez voir, c'est le code d'attaque qu'il envoie ne part pas au device réel. Ce qui est
Hmm.
une très bonne chose parce qu'on vient déjà, premièrement, de protéger le device de l'attaque. Le code d'attaque qu'il envoie va au honeypot, mais qui n'a en fait pas d'effet sur le honeypot parce que le honeypot n'est pas un IoT device. Vous voyez?
Ok. Ok, ok.
Ouais,
Ok. Ok. Ça veut dire qu'au fond, on le fait traîner sur le honeypot sans qu'il ne sache qu'il est en train d'être tourné en bourrique quelque part. C'est ça?
tout simplement. Donc,
Ok.
on fait, il perd en ressources, il perd en temps, mais nous apprenons de lui. Vous voyez?
Ok.
On
Ok.
utilise les informations, l'interaction qu'on a avec lui pour apprendre de lui, pour pouvoir
Ok.
informer l'administrateur système des failles que le système comporte.
Ok. 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 Bon, je pense que j'ai compris, mais je ne sais pas si ça répond à la question d'Idriss. Et s'il dit oui, je pense que on va, on va fermer la séance pour, vu que les problèmes de connexion persistent. Idriss, est-ce que tu peux confirmer dans le chat si on a répondu à la question? En gros, ce que j'ai compris, c'est euh, au lieu de répondre directement à la requête, en fait, on essaye de le traîner le plus possible avec d'autres réponses jusqu'à ce que, jusqu'à ce qu'on soit on apprend un peu plus sur lui ou bien on l'épuise en ressources quelque part, puisqu'il utilise forcément des ressources pour attaquer. Donc, ou même le temps qu'on fasse quelque chose. C'est ce que j'ai compris, en tout cas. Les attaques sont en max. La question, il dit les attaques sont en max. Je sais pas, je n'ai pas compris. Est-ce que tu comprends
C'est-à-dire,
comment?
non.
Ok. Idriss, si tu peux être élaboré, être plus explicite, ça va aider Volviane et ça va aussi nous aider à comprendre. I think he obviously is in the at least knows enough about the domain. Ah, ok. Oui, oui. Il says, j'avais déjà compris cela quand les systèmes s'exposent aussi au denied service sont en
Bah oui,
masse.
tout à fait, Idriss. Donc, comme tout système qui ne peut pas gérer tous les types d'attaques, notre système également s'expose à, voilà. Donc,
Ouais, ouais.
du moment où on a un seul honeypot, un DOS attaque voilà, va mettre à terre notre système. Mais pour pallier à ça, on peut simplement créer plusieurs systèmes, machines virtuelles, puisque ça ne coûte pas grand-chose.
Mm.
Et, et voilà, pour pouvoir gérer ce type de problème-là, mais toujours pas à 100%, mais
Oui.
à un certain pourcentage près.
Oui. Bon, ce qu'il faut aussi rappeler, c'est yeah, c'est une fois de plus, merci. Ce qu'il faut aussi rappeler, c'est que dès qu'on parle de sécurité, on se place dans un certain modèle précis. C'est-à-dire que là, tu es dans un certain type d'attaque précis et tu proposes une solution pour ce type d'attaque-là. Donc, euh,
Exactement.
évidemment, tu ne gères pas. Oui, ok. Et oui, il a dit une fois de plus, merci. Euh, oui, je pense qu'on va lever la séance d'aujourd'hui puisque ça fait 2 heures, 2 minutes depuis qu'on s'est connecté. Yeah, it's been 2 hours that we online. I think Volvian, you have your things. People can reach out to you if they have more questions. Maybe I don't know if you're. I think they can find you on LinkedIn and other platforms.
Yes.
Yeah.
Yeah,
So
Volviane Saphir on LinkedIn, that's fine.
yeah, feel free to find Volvian and ask more question.
Yeah.
Yeah, yeah. To say thank you so much for the amazing perseverance. Yeah, yeah. It was.
Thank you,
Yeah,
Putin.
yeah. I just on I came for last time. I hope it won't. Yeah. So thank you, Volvian. Thank you so much for persevering and throughout the bad internet. Yeah. We can see you. Yeah. Thank for last bit. Yeah. So yeah. Thank you everyone for sticking around. See you next time, next week or another week for a new session for the KmerAI talk. Bye. I'll stop the stream.
All right. Bye bye. Thank you, guys.